So my name is Chanon Pornumrod. I'm a lecturer at the Department of Chemical Engineering, CHULA University. And right now, what we are doing is we are running series of webinars trying to uncover hopefully some missing piece in the Thailand energy transition. And we are not limited to just Thailand. We hear speakers from different countries, neighboring countries, and many leading institutions to share with us what they are doing. And maybe as a Thai, we can hear and adapt to our own environment. So today we have a great, and I forgot another thing is our sponsor who give us money to do all this is the Royal Academy of Engineering, or RA Inc. This is the funding under the theme Frontier Champion. And yeah, without further ado, let me start by introducing our speakers, a good friend of mine whom I met in the University of Cambridge, Dr. Motiar Rahaman, who is now the senior researcher at the Department of Chemistry, University of Cambridge, and also a research fellow at St. John College, University of Cambridge. And today he will be discussing about sunlight-powered waste to value conversion. This is very important topic for Thailand as we have so many waste and so much biomass that we try to find a way to convert it into the value, and also in terms of circular economy. That's what we're gonna hear from Dr. Motiar, Dr. Rahaman today. So without further ado, you have 45 minutes, and we'll follow by 15 minutes of question and answers. And for the audience, if you have any questions, please feel free to just type it down in the comments, and we will pick some of your questions to put on the stage. All right, thank you very much. The floor is yours.
Thank you, Chairman. Thanks for this great invitation. It's an honor to get this opportunity to talk in this webinar here. So my talk will be mainly related to sunlight power waste to value conversion, which is, as Chanan said, it's a really hot topic nowadays, and we really think about this if we want to get a sustainable economy. So in this presentation, I'm going to mainly talk about waste. Means it's mainly talk about carbon dioxide and waste plastics, and how to mitigate and how to decrease this concentration of carbon dioxide and waste plastics from our environment and get some value-added product. Thanks again for the invitation, and it's an honor to talk here. And good afternoon to everybody. Here it's early morning, but in Thailand it's I can assume it's afternoon. And thanks for joining all. So to begin with this topic, I would like to first draw your attention to atmospheric carbon dioxide concentration. So it's a greenhouse gas carbon dioxide. We can see from due to our industrialization, it's increasing day by day. So if you see this, so this is the reading from Mauna Loa Observatory in Hawaii, US. It actually gets always continuous carbon dioxide reading. And if we see here, it's not anymore 0.04%, but it's going towards 0.43% in the atmosphere, which is a highly concerning value. It's not a good value to hear about carbon dioxide concentration, and we can see the consequences. So if we just talk about Thailand, we saw in 2023, it was a big heat wave, and it's not only Thailand, it's all over the world. We are having increasing temperature, global warming, and then an example of unusual weather condition that we have seen recently from Dubai flood. And there are many different cases that are happening all over the world. So increasing amount of greenhouse gas like carbon dioxide is not good for our environment, and we really need to think about how to mitigate that. Okay, and we have actually solution, and then the whole process actually it calls carbon capture, utilization as well as storage. So how it works actually, we can see here the carbon dioxide sources from our atmosphere, we have from our environment, and then we can capture the carbon dioxide by different means. There are different ways to capture, like using some porous material. Then we can also do electrochemical carbon capture. There are many different ways to capture carbon dioxide and then store that excess amount of carbon dioxide from our atmosphere, and then we can convert that excess carbon dioxide into something valuable. So there are many different ways how to convert carbon dioxide into valuables. Uh, for example, biocatalytic conversion, thermocatalytic, electrochemical, or even solar-driven, that is photoelectrochemical conversion of carbon dioxide into something valuable. So here in this presentation, I'm going to mainly talk about electrochemical and photoelectrochemical conversion of carbon dioxide into value-added products. Well, in the beginning, I have told that I'm going to mainly talk about two waste streams, which is one is carbon dioxide and another one is waste plastics. So plastic waste, it's a really another concerning issue for environment. So our lab, a team of our lab, they went in a plastic management sector. It was in 2022, I think. You can see Chanan here, and so this water beach waste management, they actually manage all plastic waste from Cambridge, and they try to recycle or they try to mitigate the waste plastics. And if we see some numbers, it will be really concerning and not so good to see all these numbers. So first, 1 in 3 fish caught for human consumption now contain plastics or microplastics. Production of 1 ton plastics generates 2.5 tons of carbon dioxide, because we are still really dependent on fossil fuels as our primary energy source, and it takes a lot of fossil fuels to generate plastics, polymer, and it escalates carbon dioxide in our atmosphere, which is the greenhouse gas, and we want to mitigate that. Around 12 million tons of plastics enter into ocean every year. You can see the number, which is not so good. 100,000 marine mammals and turtles and 1 million seabirds are killed by marine plastic pollution every year. And the numbers are increasing day by day, year by year. And most plastic recycling strategies and technologies are polluting and require high energy input. High energy means, quote unquote, again, the consumption of fossil fuel and escalation of carbon dioxide in our atmosphere. So we can see the values are still quite high. We are here around so now it's almost end of 2024, but to really control this issue by 2040, we have to really think about the plastic pollution. We have to reduce somehow the amount of plastic already in our atmosphere. We have to substitute them. We have to recycle the plastics, not just to try to produce as less as possible. Dispose and mismanage, we can see these two term, it is already still quite in a high amount, and we have to reduce all these things to make a real control in the plastic pollution. Okay, so what will be the solution? Just in a broad sketch, if we try to understand about waste to value conversion, how can we deal with all these environmental pollution, and then we can get a sustainable economy? So we start with these waste streams, like you can see carbon dioxide escalation here, plastic waste, and even we can take biomass. However, we are going to talk about these two only. We have different waste streams in the environment, when we can actually use renewable energy, developing different efficient catalyst material or photocatalyst materials, and then we can convert these waste streams or waste materials into something valuable, like our daily use fuels or commodity chemicals. So by these things, we can actually simultaneously do two good stuff. That one is mitigating the waste stream. Another is to deal with the current energy crisis. So we can get also some valuable or useful fuels and commodity chemical for our daily use. If we see here the current scenario, so now 2024 we have less than 26 year if we want to get a real net zero economy by 2050. So we have less than 26 year, and we have to really think now how to manage these things. So we have to replace all fossil fuels by renewable resources to get the sustainable feedstock that will actually help us to make the daily use chemicals and fuels using a renewable energy source. For example, sunlight uh, uh, here as a primary energy source if we can use. Then through sustainable chemistry, we can really make our green, like in a green way or a renewable way, we can make our daily use fuels and chemicals. And that is actually really necessary so that we can mitigate or we can decrease the amount of fossil fuels consumption, as well as it will eventually decrease the amount of carbon dioxide that is coming every year in the atmosphere. So we really need to think, and we really need to replace all the fossil fuels as our primary energy source. Well, so the the solution actually will be using renewable energy sources, taking all the waste materials, waste streams, and then try to convert them into something valuable like fuels and chemicals. Now, the scenario is clear, but actually it is not that easy to convert waste stream into something valuable. For example, here, if we want to convert carbon dioxide into valuable molecules here, I will explain a bit about these molecules. But carbon dioxide is a highly stable molecule. Itself, it has 800 kilojoule per mole bond enthalpy. So we can combine carbon dioxide with water using renewable electricity or renewable energy. We can try to convert carbon dioxide into something valuable molecules like carbon monoxide, formic acid, or hydrocarbons or alcohols. Carbon monoxide, you may ask, you may think about, oh, this is a toxic molecule. Why we need to make carbon monoxide? Because it's a good feedstock. It's a component of a synthesis gas that can be further converted into long chain hydrocarbons and alcohols by Fischer-Tropsch process. So which is it's a really important molecule. Also, formic acid, it has many different uses in our daily life, as well as hydrocarbons, alcohols we can use, or we can actually employ them as direct fuel in our daily life. So we have carbon dioxide, water, and then using renewable energy sources, we can convert this carbon dioxide molecule into something else, something valuable. But we need some efficient catalyst materials here to actually accelerate the process. What are the options we have? We have for carbon monoxide formation production, we have some heavy metals, metal catalyst, as well as molecular complexes, or even biocatalyst we can use to convert carbon dioxide into carbon monoxide. Metals, we have silver, gold, palladium, zinc type of metal. If we use in carbon dioxide conversion process, they can actually convert carbon dioxide selectively into carbon monoxide. Similarly, if we use tin, indium, cadmium, or lead type of metal, we can also convert carbon dioxide into formic acid. Enzymes can convert carbon dioxide into formic acid, like formate dehydrogenase. So there are many different options like biocatalyst, metal system, as well as molecular catalytic system, molecular complexes. So we can get carbon monoxide, formic acid. What about hydrocarbon and alcohol? There is one metal actually that can convert carbon dioxide and water directly into hydrocarbons and alcohols, multi-carbon hydrocarbons and alcohol. That is copper. Copper has an unique property that actually allows us to get some multi-carbon products from carbon dioxide conversion process. How do we design this copper material? So if we just talk about, or if we just keep uh, ourselves within this metal catalyst system. So this is a typical synthetic strategy of copper macrostructure copper material. However, this is one of the process, one of the synthesis process. We have many different other process. This one is electrochemical deposition of microporous copper. However, there are wet chemical synthesis. There are hydrothermal method for copper oxide system. Many other methods are there for nanoparticle preparation. This one is it's a unique electrochemical deposition process that allows us to get well-defined microstructure, macroporous dendritic structured copper on the electrode surface. How it works? If we see here, it's a flat surface. We can use as a substrate, and then we use a copper precursor, it's copper sulfate in a highly acidic medium, and we apply very high cathodic current density. So we generate hydrogen bubble because we have highly acidic medium, as well as the hydrogen bubble formation happens, and copper plus 2 actually gets deposited on the surface as copper 0. So we get actually metallic copper, and hydrogen bubbles, they act as a template to get this macrostructure copper catalyst. So in brief, we can see here, this is the substrate copper wafer. We get from the acid, we get protons to hydrogen under a highly cathodic condition. And this hydrogen bubble, it comes on the copper surface, and then actually copper deposition, it starts happening just beyond the hydrogen bubbles. And we can see a growth of a nice macrostructure of copper. This black stuff is the growth of our dendritic copper material or macroporous copper material. And we have very nice porous structure of copper on the planar copper wafer substrate. And then that actually is the catalyst. We can use this catalyst for carbon dioxide conversion process. So for example, if we use this copper foam, we can call it copper foam. It's a macroporous structure. We can get here around 55% of Faraday efficiency of C2 hydrocarbon. So as I told, the copper is unique for multi-carbon production. We can get around 55% Faraday efficiency. The term Faraday efficiency, it comes percentage of charge involved to form a certain product, because we electrochemically we apply a certain amount of potential, we get current, a certain amount of charge, it passes through the process, and then we actually we can calculate the percentage of charge which is involved to form a certain product. Here 55% of charge it was actually involved to form to generate ethylene and ethane, which is a really good number, which is a really nice value for selective C2 hydrocarbon production. Now, how about alcohol? Can we get alcohols also from copper? The answer is yes, but we need to actually activate the copper dendritic material. So you can see here it's as prepared copper dendrite. We can see honeycomb structure here. Then we have to oxidize the copper dendrite to copper oxide, and further electrochemical reduction of copper oxide into some nice nanostructured copper on the dendrite surface. If we get this one, then we can actually shift the selectivity of carbon dioxide conversion process from ethylene here to multi-carbon alcohol. So for example, the as prepared copper catalyst, copper dendrite, it forms quite selective ethylene around 35%. And then if we activate the catalyst and then make some nanostructure on the surface, we can get ethanol and 1-propanol, around 25% of Faraday efficiency on this activated oxide-derived copper material. So we can just see that the morphology as well as the activation approach, it's very important to change the selectivity of the carbon dioxide conversion process from one component or one product to another product. If we really want to monitor the active phase of the carbon dioxide conversion process, or like active phase of the catalyst while it is doing carbon dioxide conversion, just a brief idea I wanted to share with you here. Let's say if we if we use a copper oxide material just for the multi-carbon alcohol production of what we saw, uh, if we use copper oxide under carbon dioxide conversion process, so this is cathodic process, reducing environment, the copper oxide itself will reduce into copper zero. So the question was, uh, our question in this project was, if we directly use a copper oxide material for carbon dioxide conversion process, is there any possibility that the oxide survives under this electrochemical condition, or the oxide first gets reduced into metallic copper and then it works as an oxide derived catalyst? And so to do that, we actually did some operando spectroscopy measurements. So we can see here, this is as prepared dendritic copper, and then we oxidized the dendrite and made some copper +2 and copper +1 oxide on the surface. Then we directly use this oxide, copper oxide, as our catalyst. And we can see from operando X-ray absorption spectroscopy, around with applied potential, when we were coming from positive to negative potential, we can see here it's actually copper oxide is reducing to metallic copper. So almost at close to zero, we can get quite a high amount of copper metal on our catalyst surface. Also, operando Rahaman, it actually supports this finding. So with applied potential, from starting from a positive versus reversible hydrogen electrode, and then if we just pass the zero versus reversible hydrogen electrode applied potential, we can see all the copper oxide here. It gets reduced to metallic copper, and there is nothing, no copper oxide signal is obtained on operando Rahaman, as similar as operando X-ray absorption. So these both operando spectroscopy studies, they support actually that if we take copper oxide as a starting material or as a catalyst, it first gets reduced to metallic copper, and then this oxide derived metallic copper actually is our active catalyst material for carbon dioxide conversion process. And this process, it actually formed also some ethanol and propanol from carbon dioxide conversion. Okay, so so far we were talking about a single metal system like pure copper, but how about bimetallic system? Can we combine two metal and then perform CO2 electrolysis? The answer is yes. We can see here it's a combination of copper and indium 50-50%. If we just combine indium with copper, we can get very high selectivity of formic acid from this alloy, and the stability was quite good. So almost it was 95% selectivity and like Faraday efficiency of formic acid. It comes from copper indium alloy, and with around like 30 or beyond 30 hours of reaction activity, or like activity beyond this time. So this is 50-50. How about small amount? Because indium is quite expensive. How about adding small amount this precious metal? We see here around 4% indium. If we add in copper, it already makes a huge change. For example, we made this dendrite. It's a macroporous structure. Only 4% indium in copper moiety. We can see here at pure copper, similar structure, pure copper at low over potential. We have to note here, this is these experiments, it was done at a very low applied over potential, where copper actually gives only hydrogen, not much active at carbon dioxide conversion process, but at very low over potential. If we use this copper indium with added 4% indium, the scenario completely it completely changes. It swap the product distribution. So from 80%, close to 80% hydrogen, we can get 80% around carbon monoxide as a carbon dioxide conversion product. So this 4% indium, it makes the catalyst really active for carbon dioxide conversion process at very low over potential. So apart from morphology, the composition of catalyst is also very important in electrocatalysis to drive carbon dioxide conversion selectivity into something valuable products. Coming to plastic, what about, so we talked about different metal catalysts, metal alloy catalysts for carbon dioxide conversion. Do we have other options? What are the options for plastic upcycling if we want to convert waste plastic into something valuable? So this is another waste stream. And we can see here, if we take polyethylene terephthalate, PET plastic, which is a very common, widely used plastic, we first have to break this polymer. We can use either enzymatic depolymerization, or we can treat it like in a strong basic condition, just using a little bit of temperature for a long time. It actually gets the ethylene glycol monomer. We use this monomer to convert into formic acid or glycolic acid, which are both of them are very highly valuable product. And to do that, we have different metal options. We can use copper, we can use palladium metal, or we can combine these two metal and just simply use the copper palladium bimetallic alloy material to convert waste plastics into something valuable. Now, before coming to the sunlight driven catalytic process, now I would like to explain a bit why sunlight as an energy source, why sunlight is important, and what are the prospects of this renewable energy source as our future primary energy source. If we take a time frame of 2009 and 19, this 10-year time frame, you can see the cost of our non-renewable energy sources, coal, gas, then nuclear, they're more or less similar. It didn't change that much, but renewable energy sources like wind, it decreased quite a lot. Surprisingly, the most important point here, the cost of photovoltaics, the solar energy conversion cost, it decreased quite a lot. It's drastic decrease over the 10 years. Then we had pandemic, many different things. So many things actually changed. And then we have actually still the solar price going down, where the gas price and coal price, they're going up, slightly going up. That means with the renewable energy sources, we are doing already quite good. Solar energy is abundant. We can get almost, in Asia, it is quite available. Especially, it's abundant and already cheap, the energy conversion process, and we can definitely use this sunlight, the solar energy, for future growth through chemistry. How to do that? Next question is how we can use this sunlight as an efficient energy source. Well, we have to develop and design efficient solar devices as well as photoelectrochemical reactors. So this is an example of a two compartment integrated photoelectrochemical reactor. You can see here the compartments, they're separated by a membrane. It's a bipolar membrane. One side we have a photoelectrode, another side we have a dark like metal catalyst for plastic. This is for plastic conversion. This photoelectrode, it is for carbon dioxide conversion process. So this is actually simultaneous conversion of waste plastics and carbon dioxide using sunlight as an energy source. For plastic waste, we use a copper palladium bimetallic catalyst that actually convert waste plastics like PET plastics into glycolic acid selectively, around 95% selectivity. On the other side, when we developed this photoelectrode, we used a solar cell, and then we combined different catalysts, different types of catalyst system on the solar cell to make this photoelectrode. The idea was to combine or to connect this photoelectrode with this bimetallic catalyst. This is photocathode. This one is simple anode. It's a dark anode. We just connect these two. We shine light, and it actually drives by itself without requiring any other energy source, any other like potential or voltage or electrical energy. So what are the catalysts we used here? We attached to the solar cell. There are different systems we actually checked to demonstrate the versatility of the process. For example, we used a molecular catalyst system that actually converted carbon dioxide into carbon monoxide. We used also a bimetallic catalyst, a copper indium catalyst that converted carbon dioxide into syngas, that is a mixture of carbon monoxide and hydrogen. And we also used formed dehydrogenase biocatalyst. That catalyst converted carbon dioxide into formic acid with a almost 100% selectivity. So this system is quite versatile. We can definitely use different catalyst material to make the photocathode, and then we can transform carbon dioxide into different products in simultaneously with waste plastics reforming into glycolic acid. So this became a very first integrated photoelectrochemical system that can convert carbon dioxide and waste plastics simultaneously into valuable fuels and chemicals using sunlight as an energy source without requiring any external energy. We then thought about why to use concentrated carbon dioxide. Why not? We can think about capturing carbon dioxide and use this carbon dioxide in this photoelectrochemical system or photoelectrochemical platform to convert carbon dioxide into something valuable. So the aim of this project was to integrate carbon capture with photoelectrochemical conversion. We took the similar like photoelectrochemical setup. It is an integrated photoelectrochemical reactor divided by bipolar membrane. In the photocathode, we didn't use here different catalyst material. We used one molecular catalyst, cobalt phthalocyanine. So that catalyst can convert carbon dioxide into carbon monoxide selectively. So we used cobalt molecular catalyst here with the solar cell, and on the other side we used the similar catalyst, that is copper palladium bimetallic alloy, to convert waste plastics into glycolic acid. Instead of carbon dioxide, pure carbon dioxide, we here used captured carbon dioxide using different mediums like amine or hydroxide medium. So we passed carbon dioxide from flue gas, air, or even pure carbon dioxide through those medium. We had the captured carbon dioxide in that medium and used this medium to for our photoelectrochemical conversion of the captured carbon dioxide. We have seen even over 5 days we can get carbon monoxide and hydrogen production under the sunlight irradiation when we used even air captured carbon dioxide. So this was quite a big step forward, that even from air we can capture carbon dioxide. So this was actually we used the sodium hydroxide glycolic acid medium, and then from air we captured carbon dioxide first. We used that chemisorbed carbon dioxide, captured carbon dioxide as a reactant, and then converted that carbon dioxide into carbon monoxide and hydrogen. And it was again driven everything solely by solar energy. So this integrated device, it actually helps us to convert captured carbon dioxide as well as waste plastics into some valuable chemicals and fuels using sunlight. Next, I would like to come to the concept of an artificial leaf. So what is artificial leaf? It actually mimics the working principle of our natural leaf. So natural leaf, it takes carbon dioxide from atmosphere, water, and it produces oxygen for us, and it also makes sugar. Our artificial leaf, it's a device. It takes carbon dioxide, water, releases oxygen. Instead of making sugar, it makes multi-carbon alcohol as a fuel. And how do we design this artificial leaf device? We need to take here 2 different light absorbers. One for the photoanode, we use bismuth vanadate photoanode, nanostructured bismuth vanadate. We added a titanium cobalt water oxidation catalyst on top of it. So that photoanode actually convert water into oxygen. On the other side, we attached a photocathode. Here we used lead halide perovskite solar cell, and then we combined a catalyst to make the photocathode. So it's basically the idea was a back-to-back assembly of photocathode and photoanode, and then connecting this to photoelectrodes, shining light as a standalone device, and then we can get some interesting product. Here comes the advancement. What type of catalyst we can use to get multi-carbon product from this standalone device? We developed here a phase segregated, phase separated palladium copper catalyst. So actually palladium and copper, they form alloy quite easily. So we make first the as prepared catalyst, and by some treatment, thermal and electrochemical treatment, we actually separate the phase of copper and palladium. It is only 6% palladium with 94% copper, and then we got a catalyst that actually worked quite nicely at very low over potential. Generally, multi-carbon formation happens around 1 versus reversible hydrogen electrode, minus 0.91 versus reversible hydrogen electrode, quite higher over potential on conventional copper catalyst. We have seen here adding 6% palladium and then activating the catalyst, making them phase segregated. We can even start forming multi-carbon alcohol at 0.45 minus 0.47 volt versus reversible hydrogen electrode. That property actually allowed us to assemble this catalyst to this standalone tandem photoelectrochemical device. So this is how it looks like. So this is the Bismuth banded side where we have the water oxidation. This is the catalyst side. It's quite black. So it's the catalyst assembled or attached to the perovskite solar light absorber. So this is just two different sides of the same device. So this side, so we just immerse this device, standalone device into CO2 saturated water. We just shine light, and then this happens actually. With time from the photoanode, we can get gradual oxygen evolution, as well as with time from the photocathode, we can get along with other products, we can get multi-carbon alcohols here. Presence of multi-carbon alcohol, this is C2 and C3 together in 1:1 almost ratio. That is ethanol and N-propanol. And this becomes a very first standalone artificial leaf device that can convert carbon dioxide into multi-carbon alcohol, even C2 and C3, ethanol and N-propanol, using sunlight as an energy source without requiring any other external energy. Let me try to start this video where we can see this is the artificial leaf device immersed into CO2 saturated water, and we just shine light, and we can see the bubble formation, oxygen evolution, and from other side also hydrogen and other hydrocarbon evolution. Let me start this one if I can. It seems, yeah. You can see the bubble formation. It's coming out of of course, this is 100 times more increased speed. It is not the real speed what is showing here, but we can see some nice oxygen evolution here from the photoanode side while shining light, and it will flip actually. On the other side, we can see also some hydrocarbon and other hydrogen evolution from the photocathode side. So we just shine light on the standalone device, and it works without connecting with anything. So this is the photo cathode side now, and we can see here also the bubble formation with time. Well, okay, I go to the next one. Yeah, recently we let me take the pointer. Recently, we participated in, it was already 2022, we participated in a solar fuel competition by European Commission. The idea was to make a modular array of standalone artificial leaf device for solar syngas production. This is carbon monoxide and hydrogen from carbon dioxide under natural sunlight. So our aim was to just put this under sunlight for 3 days and to get some syngas, carbon monoxide and hydrogen. Unfortunately, we came second in this competition. We didn't get this €5 million prize, got a very nice medal, but it was a very good experience for us. And we came to know what are the precautions we should take if we want to actually if we want to bring a laboratory scale small device into a large scale industrially applicable system. So a brief overview, if we want to see here with time. So Professor Daniel Nocera from Harvard, he actually developed the first solar water splitting like artificial leaf with silicon photo electrodes in 2011. And I'm actually going to show you all the development according to my contribution, my research. During my PhD, I was actually involved in making different metal catalysts for carbon dioxide conversion process. And then I actually employed different materials and then also developed other bimetallic systems and like different hybrid materials for photoelectrochemical conversion of carbon dioxide, as well as waste plastics. Some of them are like tandem photoelectrochemical devices, standalone artificial leaf, integrated reactor, or even recently it is published a biohybrid assembly. I didn't have time to show you in Angewandte Chemi. So for solar methanogenesis. So it's quite a different versatile photoelectrochemical devices and photoelectrodes have been prepared during my time in Cambridge for this waste to value conversion. I hope I have given a broad overview in brief within this time frame. And at the end, I would like to acknowledge my team here, my research group, the Reisner Lab, Professor Edwin Reisner, supervisor, and all other team members. It's really nice and collaborative group. We are a very big group. We are dealing with many different aspects of catalysis and materials, as well as engineering to have solar fuel conversion, all the funding bodies. And thanks to all of you for your kind attention. I would be very happy to answer any questions. Thank you.
Thank you very much, Dr. Rahaman Motiar. Yeah, if you have any questions, so please, now is time. And any question from the audience, please type them down in the comments section. I believe you see my comments. Yeah, we have one question from Pirarang.
Yeah, this is a very good question actually for long-term performance. So this is so copper 0, copper 1, especially we don't actually talk about copper 2 because it gets reduced, but sometimes people actually they argue with subsurface oxide, like presence of subsurface oxygen under copper. So it depends on the connectivity of the copper material with the substrate. But generally, for long-term performance, if we just make copper oxide derived copper, the nanostructure comes on the surface, that is quite stable, and that is quite good for the long-term performance. Even if we see some poisoning on a monometallic system, that there comes actually the bimetallic, the concept of bimetallic material, adding a little bit of another metal to actually remove the possibility of the poisoning on the surface, as well as it enhances the long-term stability and selectivity. So there are different ways actually to make a catalyst selective and long-term stable. Which electrolyte will be preferable for CO2RR? It depends. So bicarbonate is quite good. It has quite good solubility of carbon dioxide. We mainly for neutral condition we use potassium bicarbonate saturated with carbon dioxide. You get around pH 7, and that's a quite strong buffer. It doesn't change. For KOH, like basic condition, you have to be careful. If you purge carbon dioxide through potassium hydroxide, it may actually reduce the pH. It may bring it back to potassium bicarbonate. But KOH is very important also, an electrolyte. As an electrolyte, it's very important if you want to do some studies at higher pH, or if you want to, especially for gas diffusion electrode flow cell studies, you can use flow of KOH with carbon dioxide. That is quite helpful as well. Uh, Yes, exactly. So when you saturate carbon dioxide with KOH, it actually comes to bicarbonate, and you have to be careful with that so that it doesn't happen. Because from KOH, you just within half an hour from pH 14, you can get pH 8 simply pH 8.3. It converts everything to bicarbonate. Is solar panel easy to recycle if we use mass scale? That's a very good question, actually. Solar panel easy to recycle. That's actually the answer should come from the solar panel community who are trying to develop different solar panels, like for example perovskite materials, um, um, uh, different lead free lead with lead, without lead perovskite materials. So they're trying to fabricate different solar cell, efficient solar cell, and also they're working on the robustness of solar cell. This, especially if we talk about our system, what we use, this lead halide perovskite, I must say that is quite sensitive towards moisture and air. So we have to really be careful on protecting that perovskite by some resin or epoxy before putting in water. So that is the drawback, actually, that you can have when you use this lead halide perovskite. But now it is advanced technology. People are working on that who are dealing with solar cell, and hopefully it will be, the time is not that far, we will be able to use robust perovskite materials with good recyclability.
We got another two more questions.
Yeah. Uh, Considering the timeline of developments of photoelectrochemical devices and related technologies such as the integrated photoelectrochemical reactor and the standalone artificial leaf, what specific insights or breakthroughs from your recent work do you believe will most significantly impact the efficiency and scalability of uh, excellent question again. Yes, so the development, actually, small development will accumulate, and at in one time, I think in near future we'll be able to bring it to that level. I would say a few things point by point to bring it really in the industrial level or in a large scale. uh, the bottleneck, the main issue here. So for just to give you an overview, we are doing in laboratory scale experiment with a small like photoelectrochemical reactor with maybe 1 centimeter square device. Now to bring it to the large scale, we have to just increase the size of the device. In terms of catalyst, what we are using for plastic reforming, let's say copper palladium, you can make or you can fabricate in large scale, even meter square. That will not make any problem. The problem here is the light absorber. The light absorber, the solar cell fabrication in large scale or in a big like size, it is still kind of like under development, I would say. It is there are many different positive news. You can see, you can go to literature, and almost every week you can see the improvement in efficiency of the solar cell. It is coming, so people are working constantly, and we hope that we will find a robust way to make or to fabricate some efficient light absorber that can be just replicating in a large scale. So once we have that light absorber in large scale, we just simply add the catalyst, both for carbon dioxide conversion as well as plastic reforming. We fabricate the catalyst. Simply, if you make like a few grams of nanomaterials, you can just fabricate a meter square of your catalyst substrate, and then you can attach that large scale catalyst to your photoabsorber and simply do the experiment to make it bring it to the industrial level.
Do the magic.
Still, I should not say that this is going to happen tomorrow. It will take some time, but the progress is really good. I can see the slope is really steep. It's going up, and hope we will find something in near future. uh, Additionally, how do you envision the role of collaborative research in accelerating the transition from this innovative concept to practical large scale? Yes, yes, this is very important. Yes, so we should not. That's the reason we actually wanted to participate in the European Commission, this solar fuel competition. It was the idea of that competition was to make a meter square prototype device to generate solar fuel under like natural condition. So to do that, we had to collaborate with different like expertise, and I really, this is very important. I really feel that you should not confine yourself in your laboratory scale. If the industry collaboration as well as collaboration with different expertise, it's a must to actually combine these innovative aspects and with some large scale implementation, the possibilities of large scale implementation, and then the progress should go together. So I would say, and I personally feel it's a good collaboration between academia and industry that will actually help us to bring this technology further. It's very important. Yes.
All right. I guess we should wrap up for the session. So let me thank you again for joining us, spending your morning with us at the Faculty of Engineering, Chulalongkorn University. I hope that I'm sure that our community benefit greatly from your talk, and hopefully we have a chance to work together in the near future. Yeah, Professor
Looking forward.
Anomnath
Thank you.
also say thank you very much. She is actually the 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 the, the head of this project,
Yeah.
and yeah, it was really nice to hear your story and your contribution to the field, and to see how you started from just purely electrochemistry, moving towards solar driven, and now moving to your next things. And it was really nice to see all this. And yeah, thank you so much for sharing all the story, all the research, all the inspiration with us. Yeah, this session will be uploaded on YouTube later, and yeah, you can always come back and hear your people can always come back and hear your talk. All right, thank you very much, Motiar. Any last word from you?
Thank you. I really enjoyed. I must say I really enjoyed this whole session, and I would like to thank you and the entire engineering department for this invitation, for this kind invitation, and yeah, looking forward for future collaboration. And yeah, good luck to you too. Thank you very much. Bye bye.